All right, everyone, welcome to SQL Bits 2020. This session is deploying SQL Server in Kubernetes. I'm Anthony Nocentino. I'm a consultant and trainer and founder of Centino Systems, where I specialize in system architecture and performance. I've been a data platform MVP for the last couple of years, and I'm also a friend of Redgate. So here at the bottom, you can see my contact information. There's my email address. If you have any questions about today's session, please feel free to hit me up via email. I'm also on Twitter, where it's my main way to interact with the community, so please follow me on Twitter if you aren't already. And I also blog pretty frequently at centinosystems.com/blog, where I cover topics such as Kubernetes, SQL Server on Linux, and PowerShell on Linux. Now, I'm also a Pluralsight author, where I have a whole series of courses on Kubernetes, on Linux systems administration, and also SQL Server on Linux. So check me out on there if you want to dive deeper into a lot of those topics. Now, let's look at what we're going to cover in today's session. We're going to talk about deploying a SQL Server in Kubernetes. And the first thing that we're going to talk about is data persistency and how to store data inside of Kubernetes clusters. Then we're going to look at pod configurations and what it takes to run SQL Server inside of a pod. Basically, what's the code needed to get this up and running and how it all pieces together when our container starts up inside of a pod, inside of our Kubernetes cluster. Then we're going to look at disk and resource configurations, where we'll look at more advanced disk topologies for using SQL Server inside of Kubernetes, and also resource configurations, so we can establish what are called limits and requests, basically guarantees for resources in our cluster in terms of CPU and memory, and also upper limits, or the maximum amount of resources that can be consumed. So very valuable when it comes to running tier 1 workloads inside of our Kubernetes clusters. Next up is backups. Of course, a key concept core to most data professionals' hearts, and we'll discuss how backups work inside of our Kubernetes cluster. And then we'll get into what I used to call the future of SQL Server in Kubernetes, but we'll talk about the present of SQL Server and Kubernetes, and we'll look at some of the solutions that are being developed by the SQL Server product team at Microsoft based on Kubernetes. And so first up, let's look at running SQL Server inside of Kubernetes. And one of the key concepts that I want you to understand is that when we deploy a pod inside of a cluster, it's going to go back to the initial state of that container image each time a pod is started up. And so as a data professional, that's very unique because, well, one of our key jobs is to keep data around. And how are we going to be able to then keep the state of our application independent of this life cycle of the pod? And we'll learn some techniques about that throughout today's session. We're going to learn on how we can manage state and storing that data external to the pod, but still giving that pod access to that data in our persistent storage. And then we're also going to learn how we can decouple configuration, and so we can affect configuration in code so that we can control our app's configuration, or more specifically, our SQL Server's configuration. So let's look at the standard way to roll out SQL Server inside of Kubernetes using the Kubernetes API construct called a deployment. A deployment in Kubernetes has the responsibility of defining the desired state of our application. So in our deployment, I'm going to tell it things like which container image to run, or how many SQL servers that I want it to run at any given time. And we're also going to define the configuration elements of our SQL Server instance, or the SQL Server pod itself. We're going to dig into the code of that a little bit later, but in this part of the presentation, I want you to focus on kind of the big picture concepts of what a deployment provides inside of a Kubernetes cluster, specifically within the context of running SQL Server. So we create this deployment object, and that deployment has the responsibility of starting up a replica set. That replica set has the responsibility of starting up a pod somewhere in our cluster. And so in this case here, you can see we start up a SQL Server, maybe perhaps version 1. Now, we also inside the deployment define the storage associated with this particular pod that we want to have started up. And so the storage will be allocated and attached to the pod and exposed into our application at a particular file system location. And we'll learn the implementation details of that momentarily. Now, we also will expose access to our SQL Server running inside of our Kubernetes cluster with a service, where we'll define both a TCP where we'll define a protocol such as TCP and a port, in this case, 1433. We'll point users and applications at that persistent IP address that the service provides, and that service will load balance that request into the cluster to get access to that pod that's running in our cluster. Now, one of the key concepts that we get kind of in the desired state philosophy of how Kubernetes treats pods running in a cluster is, well, we tell Kubernetes to run one SQL server all the time in our deployment. Now, if something goes wrong in our cluster and that SQL Server pod dies, well, it's the responsibility of the replica set that was started by that deployment to ensure that there's always a pod up and running somewhere in the cluster. So if our application crashed, or in this case, SQL Server crashed, the pod will then be restarted by the replica set. If the node dies, then that pod will be scheduled on a node somewhere else in our cluster. So we get failover cluster-like functionality out of the platform, in this case, Kubernetes. Now, inside of that deployment, if I need to affect some change to my SQL Server, maybe a new version of SQL Server comes out, and I want to go from, in this case, V1 to perhaps V2, or more accurate, let's say maybe like go from CU5 to CU6 for SQL Server 2019, like we're going to do in our upcoming demos. I'm going to change the code associated with that deployment and feed that information into our Kubernetes cluster, and Kubernetes is going to do this. What it's going to do is define another replica set in our cluster. It's then going to shut down the running pod in our cluster and then start up a new pod somewhere else in our cluster and attach the storage to that on that new version of our application. And we're able to affect these changes by changing code. So in this case here, moving between two versions of SQL Server, potentially minor versions like cumulative updates, but also major versions can be rolled out in this way as well. Now, there are some nuances to this. As you can see, when we rolled that change out, we made sure to shut down SQL Server first before starting up the SQL Server. And that's called a rolling, or that's an update strategy called recreate. The default is rolling update, and we'll look at the code to make sure that we defined the right update strategy later on in this session. Now, we also see that we have the old replica set still defined. Kubernetes deployments will by default keep 10 versions of replica sets around. And so what that's valuable for doing is giving us the ability to roll back. So if you're within cumulative updates inside of a version of SQL Server, you can literally roll back to a previous version by just undoing that change. So very valuable functionality there. So now that we know kind of the high level picture of how SQL Server is deployed inside of Kubernetes using deployments, let's dig a level deeper and start talking about how we store persistent data inside of Kubernetes. There's a Kubernetes API object called a persistent volume. A persistent volume is administrator defined storage. So basically, this is going to be infrastructure specific stuff that we're going to work with our cluster administrators to define. And so because we're going to have some physical storage constructs available to us either in our data centers on-prem or in the cloud. The types of storage that we have available to us. So here's kind of a short list of those. We have iSCSI, NFS, Fiber Channel, Azure Disk, and many, many more based on your cloud provider and other different types of storage. Now, one thing I do want to call out is that storage is rapidly changing right now. There's a drive towards some standardization called CSI, or the Container Storage Interface. And so we're really seeing some maturing in this space. And so keep an eye on that. What you are seeing is some integrations from storage vendors that are available in the market that are working better with allocating storage inside of your cluster. In kind of the legacy ways or the old ways, you would have to work with your cluster administrators to define your storage, but we're definitely seeing this change as things go forward and integrations are happening between Kubernetes and storage infrastructure. Now in the cloud, that's kind of been there since day one. I can just say, hey, give me an Azure disk, and Azure will give me a disk. And the way that we do that is with what's called a persistent volume claim. A persistent volume claim is kind of a way to decouple the configuration of the actual storage from the application's request, right? So the claim is like, hey, I just need some storage. And so our pods will make a claim of the PVC. So in our pods definition, we're going to say, hey, you know what? I need some storage, and I'm going to define this claim. Inside that claim is where we'll define what we want. I want some amount of storage of some type. So maybe 100 gigs of tier 1 SSD or whatever it is of the type of storage that's available to us. Now, that PVC is going to then work with our cluster to map that back to an actual persistent volume, like the real storage, either in our data center or cloud. And the motivation behind this is it really gives us the ability to decouple the pod's configuration from the storage's configuration. So inside the pod definition, I'm going to say, hey, I just need some storage. Inside the claim, I'm going to say how much and what type. And inside the persistent volume, that's going to be the actual infrastructure specific configuration of the storage that I want to consume. And so now that we know what persistent volumes and persistent volume claims are and how we can get access to persistent storage in our cluster, let's look at how we can map that back into SQL Server so SQL Server can use that storage and we can add some persistency to our pod-based application, in this case SQL Server, independent of the lifecycle of the pod. And so we're going to define persistent volumes and persistent volume claims, right? Just basically, we're going to ask for some storage inside of our cluster. Now that storage is going to be allocated into the instance directory inside of our pod. So that's where we'll find the error log, the default trace, and all those other things. And that's going to be in the file system location, var opt MSSQL. And inside of the pod, basically, if you think about what we're doing, we're saying, hey, give me this storage, and I want to attach it to this specific file system location inside of my pod. And that's kind of the key way on how we're going to decouple those elements, the life cycle of the pod and the storage itself, by mapping that disk into the pod inside of our container. Now, in addition to the instance directory, the default user database directory is a subdirectory of var opt MSSQL/data. Now, we can define custom directories if we want to and position additional disks at those file system locations if we want to, and I'm going to show you an example of that a little bit later. But since the default database directory is a subdirectory of var opt MSSQL, if we park one disk at that location, then all of the databases associated with this particular instance will be written to that same persistent volume. So inside of var opt MSSQL, like I said, you'll have the error log, the default trace, all of the instance configuration, the system databases, etc. And inside of var opt MSSQL data, that's where you'll find the user databases. Well, actually, the system databases too will all be under /data. And now we're going to look more detailed about how we can get additional disks added at other file system locations later on in the session. Now let's take a look at some code examples of how we can define persistent volumes and persistent volume claims inside of our Kubernetes clusters. When we're talking about persistent volumes, that's going to be the infrastructure specific information about the storage that we want to have access to. Now, when you're using what's called static provisioning, you'll have to define this object yourself. And what I want to call out here is core to what the kind of the idea behind a persistent volume is. It's going to have the infrastructure specific configuration for your infrastructure. So here you can see I have the spec, and inside the spec, I'm defining a type NFS and also the server location and path. So very specific to my infrastructure. This is key to kind of how we are going to use this in our production scenarios, because this will have to be applied to your environment, right? If you're using iSCSI, Fiber Channel, whatever it is, you'll have to work with your cluster administrators to get this storage provisioned. Now, again, that's going to be specific to your infrastructure in on-prem scenarios. In the cloud, you can use a technique called static provisioning, in the cloud, you can use a technique called dynamic provisioning. And what dynamic provisioning will do is we'll go and create this persistent volume object for you automatically without you having to worry about the infrastructure specific configurations. What we're also seeing on-prem is storage providers integrating with Kubernetes better, such that they will be creating these persistent volumes for you dynamically without having to go to this level of very infrastructure specific code. Now, the key point here is if I have to go and build this for a customer, really what I'm going to do is go and read the documentation that describes the storage type, in this case NFS, and then the implementation details about that. And so that's kind of the key takeaway there is you're going to have to work with your cluster admins to kind of color this detail in. Now, for the persistent volume claim, that's where we're going to describe what we want, right? In this case, I want 10 gigs of storage from my cluster. And so there inside the resources and requests, we can see the amount of storage that I'm requesting. Again, in a static provisioning scenario, these two will be mapped together by the cluster when I define both the persistent volume and the persistent volume claim. In the cloud or in those dynamic provisioning scenarios, in the cloud or even in the ones on-prem where those storage providers are starting their integrations with our cluster, we can use claims to dynamically allocate the storage for us. So I could just say, hey, give me a 10 gigabyte disk inside of Azure, and Azure will allocate a 10 gig disk and attach that into my pod for me. Similarly, on-prem, we'll get volumes provisioned for us inside of our storage systems. And so let's bring that together and discuss how we can leverage those persistent volumes and persistent volume claims in the context of running SQL Server specifically. And so inside of our pods configuration, we'll define our storage configuration, both the persistent volume claims and the persistent volumes. In Now, during that initial pod deployment, the very, very first time that SQL Server starts up, it's going to look and see inside of VAR-opt MS-SQL that there's no system databases there in that default data directory. And so since there isn't anything there, what's going to happen is SQL Server is going to copy the default, or excuse me, SQL Server is going to copy system databases into that default data directory from this thing called an SFP, or a single file package. Now that's kind of core to the design of SQL Server on Linux. You'll see this in native SQL Server on Linux implementations. Now, once that data is copied into VAR-opt MS-SQL data, it's actually written to that back-end persistent volume storage, right? And so now we have those two things separated. We have the pod, which is up and running in our cluster, and we have data that's stored on some physical disk somewhere, right? In my lab here, we're going to see that written into an NFS server. Now, on subsequent pod deployments, right, that storage is going to be attached into that pod. And so even though we might be pulling a brand new container image from the Microsoft Container Registry and starting that up, what's going to happen is SQL Server is going to start up and it's going to see it's got a master database there. That master database is going to have the definition for all of the user databases, and everything's going to come back online if everything's available to it. And so once master is read, that's going to define our instances configuration, right? With regards to what elements are configured. It's also going to define the state, like which databases need to be brought online. And if they're on multiple disks, potentially, well, if those disks are all available, those databases will be online and everything will be up and running. And so that's key to how we've decoupled the lifecycle of our pod to the actual state of the system, because all of that data is going to be written externally into the directory of VAR-opt MS-SQL, but that directory is actually back-ended by storage that's independent to the pod itself. So now that we know how we've decoupled the state of our system from the lifecycle of a pod, let's look at how we can configure our system or our SQL Server inside of our deployments that we use inside of Kubernetes. So inside our pod's configuration, we're going to define a collection of environment variables. And when SQL Server starts up the very first time inside of a pod, right, that first time before it has any information stored inside of the master database that might be on persistent storage, that very first time, we need to be able to inject some configuration. And environment variables are a core way to do that. And so two key environment variables that we have to have that very, very first time we start up SQL Server inside of Kubernetes is accept EULA and also MS-SQL_SA_password. So accept EULA is going to define whether or not we accept the user agreement, and then the SA password is actually used to set the SA password inside of the database system. So SQL Server will start up the very first time. It's going to do that process of distributing the system databases into the persistent storage. It's going to go and it's going to read these two environment variables from the runtime environment inside of the pod. It's going to accept the EULA, and then it's going to set the SA password and store that inside of our system databases. Now, in the code that we use to deploy SQL Server, we can define those values statically inside of that code, but for EULA, that's okay, right? That's just a static value of yes or no. Well, usually it's going to be yes, or the actual individual character Y. But for MS-SQL_SA password, well, we don't want to have that configuration inside of our actual deployment that we're using inside of our cluster. So a common technique to decouple that is to store the actual SA password as a secret inside of our cluster. And so when the deployment is deployed, it'll get access to that secret, it'll pull that password and store that value inside of the environment variable. So that's a good way for me to be able to write code and exchange it with potentially untrusted other users of a system without having to expose my SA password. Now, what's key here is that pods, and we've discussed this a couple of times, is that pods are going to go back to that initial state of the container image on creation or on deployments, right? Well, that second time is what we really want to focus on here, right? Because this environment variable information, a lot of it's going to be persisted inside of master or inside of the actual databases itself or the system databases. And so the first time this happens, yeah, it's going to read those values. The second time it's going to see, well, hey, I have a collection of system databases, an SA password's already set, and then it's going to go and start up that normal SQL Server startup process. Now, when it comes to environment variables, what we have access to is a huge collection of potential configuration points for us to assert that configuration inside of our SQL Server deployments. And so here is a link to the environment variables that surface those configuration elements. And one of the ways that I like to describe this to people is that pretty much, I'm generalizing here, but pretty much anything that you would configure in the SQL Server Configuration Manager or inside of Windows in that MMC snap-in is going to be exposed as an environment variable for you to be able to configure here. So things like starting up SQL Agent, specifying a TLS certificate, things like that are going to be defined inside of environment variables. All right, so let's bring all of that together and look at how we can define SQL Server in YAML, right? The core way that we're going to deploy SQL Server inside of YAML is to wrap that up in what's called a deployment object inside of Kubernetes. And so here we can see the YAML code associated with the first part of that. I'm going to walk through the key elements as we walk through this slide together. I don't want to throw like the 100 lines of code at, maybe like 30 or 40 lines of code at you at one time. So at the top left here, you can see that the API version is app/v1, the kind is a deployment, and we're giving that deployment a name, which is MSSQL deployment. Inside the spec is where we define the implementation details of the deployment itself. Now, key here is replicas 1. And what that is that's going to give us that functionality that we looked at earlier in the session, where Kubernetes is going to guarantee, if it can, to always keep one SQL Server up and running for us at any given time. Now, if I needed multiple SQL servers, I would create another deployment to create those other SQL servers, perhaps multiple instances or multiple application deployments, things like that. So you would not use the same individual deployment for those scenarios. You would just create another deployment for those multi-instance scenarios. Now here we also see strategy type recreate. That's going to give us that functionality where it shuts down that SQL Server pod first before starting up the other one. And that's valuable because, well, we can't have two SQL Server pods potentially up and running at any given time. And the default update strategy is a type called rolling update, which rather than shutting down the pods first, it'll start up a collection of pods first and then start shutting down the old pods. And that's valuable in stateless applications because then you're kind of having a zero downtime transition between the old state and the new state of the application. In a relational database system, we certainly only want to have one pod reading and writing files at any given time. Now, SQL Server is smart enough to figure out that it was unable to get an exclusive lock to the file, and it'll handle it, but this is a way of dealing with that gracefully rather than having the pod crash because it couldn't get an exclusive lock on the files. Now, inside of the pod spec, kind of jump over on the right here, we're going to define a security context and specifically an FS group. Older versions, but the initial implementations of SQL Server ran inside of containers ran as root. And that's not exactly the best security practice. And so the product team worked to get SQL Server to run inside of a container to run as non-root. And what this does here is gets us the ability to make sure that our non-root container has the ability to read and write the files that are stored on those persistent volumes. Now, inside the container section, this is where it's going to look a lot like how we would deploy a container, where we're going to define a name and then an image. So I've abbreviated the text there, but here you can see the image or the specific version of SQL Server that I want to run is 2019 CU5 on a base image of 1804. Now the container ports are going to be 1433. That's running inside of the pod. We still need to expose that with a service so people can access this particular application outside of the pod and outside of the cluster potentially. Next up, we define our environment variables. We'll specify a name, except EULA, and a value of yes, or an individual character of Y. Now for the SA password, we're not going to specify that inside of the actual deployment YAML itself, because if I gave this code to you, the last thing I want to have is my actual SA password in this code artifact. Well, what we can do is we can read a value from our secret key ref, which is our cluster's secret store, and we're going to read a specific key named MSSQL, or excuse me, a specific secret named MSSQL, and then a key inside of that secret of SA password. And then the value of that will actually be stored in this SA password environment variable that we exposed inside of the runtime space of the pod itself for our application process to be able to read. The volume mounts are going to define what volumes are going to be exposed where. And so here we see we're going to have a volume named MSSQL DB at the mount path varopt MSSQL. I'm going to put a volume named MSSQL DB of a type persistent volume claim with the claim name PV SQL data at that location. That PVC SQL data is the claim that we looked at a second ago that then went back to the persistent volume that was our NFS storage. So that's kind of that lineage there. The persistent volume goes to the claim, right? We define those two objects in code. Inside the SQL Server deployment, we define, hey, you know what? I want to use that persistent volume claim and mount that persistent volume claim at var opt MSSQL. So now when SQL Server starts up, it goes through all those processes that I described a second ago. Basically, the first deployment, it drops down a master database, reads these environment variables, and writes that all out to that actual persistent storage. So now that we know how SQL Server is deployed, let's look at kind of the next level. We're going to look at advanced disk topologies for SQL Server. And so what if I wanted to take additional disks and put them inside or expose them inside of the pod so that I can do things like maybe have high-speed disks for a highly transactional database, or a particular disk type for transaction logs, or maybe larger disks for a database that just needs some storage. All those different things that we might potentially need to do with those more advanced disk scenarios that we're used to using inside of traditional implementations of SQL Server on servers or virtual machines. Well, what you're going to do is you're going to define the storage subsystem using the same tools and techniques, right? You're going to define persistent volumes if we're using static provisioning, and we're going to use persistent volume claims either way. Then we can configure some environment variables to specify the default data and log directories at startup. Those environment variables then will give values that say, you know what, I want all of my databases by default to go to /data or whatever that is. And I also want all of my log files to go to /log or whatever path that is. And it's up to me to make sure that there's going to be disks, it's up to me to make sure that there's going to be disks attached at those file system locations. And I could blend different types. Now, these are for the default data directory. So this is no different than if you went and configured the default database directory or log directory on any SQL Server instance. This is just how we're able to inject that configuration into configuration of our pods. We of course could attach those disks, not make these modifications, but when we created a database, we would just need to specify the the data file and log path in the actual database's create database statement. But if we're doing it this way, new user databases will be created at these locations. And so when SQL Server starts up that very first time, or potentially multiple times, all those persistent volumes and persistent volume claims will be mounted inside the container, right? Whether we have one at /var opt MSSQL data, one at /data, and one at /log. It's the job of Kubernetes to make sure that they're all attached into the pod and mounted at the correct locations inside of the file system. Then what's going to happen is master is going to come online, right? It's going to see the pod's going to start up. It's going to be like, you know what? There's a master database there. That's cool. And if there's any user databases into that particular environment, if those disks are attached, those will be online and we'll have access to our data. And so using this technique, we can build more advanced disk topologies, exposing different types of disks potentially, or multiple disks into our cluster. You'll see a lot of demonstrations that just show how to expose one disk. That's great for demos, but it might be the case that we need more advanced scenarios. All right, so up next, let's look at resource management inside of Kubernetes, kind of a key topic for us to be able to really define the quality of how our application or how SQL Server is going to be deployed so that we can control access to resources in our cluster, specifically CPU and memory. Now, we have the ability to assert control over resources at the pod level. And so when I say resources, I really mean CPU and memory, because what we're going to be doing potentially is running multiple workloads and even multiple SQL servers inside of a Kubernetes cluster. And we need the ability to kind of control who gets access to what, so that again, we can maintain the quality of the performance of our application or our SQL servers that are running in our cluster. And Kubernetes gives us two key ways to control resources in our cluster, and those ways are requests and limits. Requests are guarantees, right? I can request that I want 4 processors for this particular SQL server to run and exactly 16 gigs of RAM. And those are guarantees. If those resources aren't available in the cluster, then that pod won't get started up. I'll need to make an adjustment and reduce the size so that I can find those resources somewhere in the cluster. And that's the responsibility of Kubernetes to find a node that has those resources available in a cluster. So in that example, 4 vCPUs and 16 gigs of RAM. Now, on the limits side, limits are upper boundaries. So I can say, and you're going to see this kind of mostly on the memory side of the house. You can say, you know what, don't consume more than this much memory. Maybe it's 16 gigs of RAM or 32 gigs of RAM, because I want to establish an upper boundary so that I can control how much memory SQL Server is going to consume at the system level. Now, we do have the ability to use instance level settings to control that, and I'll talk about that in a moment. So requests are guarantees, limits are upper boundaries. Neither of them are defined by default. We have no limits or requests by default, which can put us in some interesting scenarios if we don't define, especially a memory limit. So specifically when it comes to SQL Server, when it starts up, if you don't define a memory limit, SQL Server is just going to read the available amount of memory that's in a node. So if that node's got 128 gigs of RAM, it's going to try to access all 128 gigs of RAM. If I set a limit to 16 or 32, whatever it is, SQL Server is just going to see that amount of memory when it starts up. And that's key because if I have multiple pods that are in that particular node that might be fighting over that memory, that could put me in some interesting scenarios where I could potentially run out of memory and cause an out of memory condition, and a pod can get terminated inside of my cluster. Kubernetes by default, actually not by default, but Kubernetes doesn't really have a concept of swapping. The philosophy behind that is that it's better to just kill the pod that's misbehaving and consuming a bunch of memory and protect the overall health of the node rather than start swapping and drag the whole system's performance down. The key idea here is, though, we really need to think about when we're deploying multiple workloads inside of a cluster and the resource allocation there. And so that's where limits come into play. From a code standpoint, it looks like this. So we have inside of our pod template spec where we defined our containers. We give that container a name, an image, and then we'll define the resources that we want associated with it. And so if we had a request, we can define that like a CPU. Here we see 1, memory 1 gig. And so that's a guarantee. Like for this pod to start up, it has to find those resources somewhere in the cluster. If those weren't available somewhere in the cluster, then this pod won't get started. Now on the limits side of the house, we can use this syntax here. We'll define a limit. And then let's say we don't want this pod to exceed more than 4 gigs of RAM. SQL Server starts up, it's just going to see 4 gigs of RAM, even if that node that it started up on had 128 gigs of RAM in it. As we discussed a second ago, server instance settings still apply. So in this specific scenario, if I said, hey, SQL Server, you can't use more than 3 gigs of RAM by setting max server memory, then, well, SQL Server would only consume up to 3 gigs. The idea here is that my suggestion to you is to set both, right? Set that upper limit in the pod configuration and also set max server memory like you would if you were using a multi-instance failover cluster. In those scenarios in those scenarios where you would use maybe Windows Server failover clustering and run multiple instances across multiple nodes inside of a failover cluster, you would do that math to figure out what was the max server memory that I'd want each node to use in the sense that so I can maintain the quality of service. Key difference, though, is in that Windows scenario, SQL Server and the underlying OS Windows would kind of balance each other out, right? SQL Server would evacuate its caches and release the memory back to the OS. And that functionality exists inside of Linux and inside of Kubernetes specifically, but it's not exactly the same. There are some scenarios where you can assert a lot of memory pressure very quickly and cause bad things to happen and cause SQL Server to run out of memory and potentially get killed. So just make sure that you're doing the math when it comes to the memory allocations inside of your cluster. That's a key design philosophy there. All right, so near and dear to every DBA's heart, backups. So let's get into that. When it comes to running backups, the core thing for me when I run backups in any system is to get my data onto disks independent of the actual primary data files as fast as possible. Basically, if I'm using this backup, or if I'm using this array here, I want to get it off of that array and onto another storage subsystem as fast as I can. And then from there, I'll go and replicate it offsite and do whatever. That's all the same inside of Kubernetes. But we're just going to talk about kind of the way that you can build that infrastructure specific inside of Kubernetes. Now, we can do a couple of things, right? We can attach a persistent volume into our pod and back up to that. And that volume can be shared amongst nodes or potentially dedicated to an individual node. And so I can expose storage to multiple nodes in my cluster, right? Or I can expose storage to multiple pods in my cluster, and like I'm using today, and run SQL Server backups all into that one storage subsystem. If that's what I want to do, that might be an NFS share. It could be an Azure disk. It could be any of those backup targets. It could also be dedicated. I could leverage an individual disk. Maybe if I need to control the quality or how fast those backups occur, I can allocate a specific disk inside of a pod for backups. So again, shared or dedicated, either one can be done. The types of disks that are available to us, I talked a second ago about the Azure disk scenario. If we're in Azure, we could also use Azure Files and mount that as a CIFS share. If we're on-prem, we can use NFS, iSCSI, or Fiber Channel. Again, any way that I can attach a disk into a pod, right? That's just using that storage construct of persistent volumes. In addition to that, it could go back up to URL. And that's really not anything to do specifically with Kubernetes, but just knowing that we can leverage standard SQL Server techniques to back up our data. So we can back up to URL if we're in Azure or potentially even on-prem. How do I drive the backup workload? Well, that backup workload is going to be driven with normal techniques, right? I can use backup database statements in T-SQL, or I can use the stuff that I'm used to using. I can use Ola Hallengren scripts to drive SQL Server agent jobs. I can use maintenance plans, all of those different things. And my personal favorite, is to use DBA tools. And we're going to see that in our upcoming demos. And so we can leverage all of the standard stuff that we're used to doing to back up our databases. But for me, again, that key concept is, how do I get my data onto another storage subsystem as fast as possible, right? So we can meet our recovery objectives. All right, so that's a lot of theory that we just went through. Let's kind of dig in and do all of these things. And so we're going to deploy SQL Server in a deployment inside of our cluster, leveraging persistent storage. And then we're going to walk through some additional scenarios where we're going to deploy an advanced disk topology. We're going to set some resource limits and see how that comes into play, look at some high availability and also some backup options. All right, so here we are in VS Code. And what we're going to do is we're going to walk through the process of deploying SQL Server together. And the first thing that we're going to do is create a secret. And so I'm going to load up this environment variable here on line 6 so that I can use that over and over in our demos. On line 7, we're going to use kubectl create secret of type generic and give it a secret named MSSQL. As for the key value pair in there, you can see SA_password equals $SA password. So it's going to read my environment variable, create that secret, and keep my SA password in that secret inside of my cluster. Now on lines 13 and 14 here, we're going to have our deployment. We're going to have a deployment of our, on lines 13 and 14 here, we're going to have the code that's going to create our persistent volumes and the persistent volume claim. So let's go to run that code together. And at the bottom here, you can see it created a collection of persistent volumes and a collection of persistent volume claims. Inside those YAML files, you'll find that we have the implementation details of the persistent volumes and the claims. And so we have here, if we scroll down a little bit further, similar to what we looked at in the presentation portion here, is we have the implementation details of the persistent volumes. So there on line 13, we can see this is of type NFS. We can see my server IP, and we can see the path to those data, the path to that NFS share. And so that's going to be the implementation details for my storage subsystem. If you're going to go do this demonstration on your own, well, you either need to make sure that there's an NFS server at that exact location, or you're going to modify this file for your infrastructure specific configuration when you're using this type of storage. Now, again, in the cloud, you have dynamic provisioning, which means you don't have to declare the persistent volumes. You can just declare the persistent volume claims, and Azure will go or any of your cloud providers will go and allocate those disks and expose them into your pods when you reference them in your deployment. So what we're doing here with these persistent volumes and persistent volume claims is what I'm going to do is position a disk, or in this case, an NFS mount, at 3 different places. One for my system directory, right? So the error log, things like that we saw when we discussed how that's all laid out. And then we're also going to have one for our user databases and our transaction log. Also in that system, persistent volume will be our system databases. And we'll see how that all pieces together momentarily when we get into that demo. So let's go ahead and roll out SQL Server. And I'm going to do that with kubectl apply -f. And then the YAML file is deployment advanced disk.yaml. Run that code there. And at the bottom, you can see we have a deployment was created. And I also exposed it as a service. And while that's doing its thing and getting deployed, let's look at deployment advanced disk.yaml and see what we got going on there. So inside of here, very similar to what we looked at in the presentation portion, we are defining a deployment, we're giving it a name, and we're saying, you know what, Kubernetes, always keep up one SQL Server all the time. We have our update strategy as recreate. Jump down a little bit further. Inside the container section, we can see our environment variables. So there's accept EULA, and then also the SA password, which is being read from the secret that we just declared a few minutes ago. We're also just saying that we want our SQL agent to be started up with this environment variable here. And I'm also declaring that I want the default data directory and the default log directories defined as /data and /log. In volume mounts, I'm defining 3 volume mounts at 3 different file system locations. For the system volume, right, we're going to mount a volume named system at the varopt MSSQL file system location. Again, SQL Server is going to start up the very first time. It's not going to see anything there, and it's going to drop down all the required files, including the system databases, grab that environment variable, and set our SA password. And that's all going to happen in varopt MSSQL. You can see from the syntax highlighting here that that volume for system is going to reference the volume that we've declared here on line 46, and that's going to use a claim named PV-NFS system, which is the claim that we just declared. We ran the code to create the persistent volume and a persistent volume claim. Moving forward, we see the other 2 disks that we're claiming. So we're bringing in PVC-NFS data as the data volume. That's going to get mounted at /data. And same thing goes for log. That's going to get a volume named log from the claim, PVC-NFS log, mounted at /log. And at the bottom here, we're defining our service type. So that should be up and running, hopefully, after walking through that file. If I do a kubectl get pods, we can see that our deployment is up and running. That means SQL Server has started and it's done its thing. So let's kind of poke around and get access to that SQL Server. If I check for the IP information, here we can see my deployment is listening on this cluster IP ending in .100, and it's listening on port 1433 and also 32024 for a service type called node port. So let's grab that cluster IP information and store that in an environment variable and echo out that information to make sure everything's loaded up correctly. And so there we can see I have those environment variables set. I use environment variables so that I can repeat this demonstration over and over and over again and not having to copy and paste to lots of things around with regards to when values change. So let's ask SQL Server what its name is. Right? So SQL Server say, you know what, give me your name and give me your version. Run this code here. What do we got? We're running a SQL Server 2019 CU5. Right? You can see that over there on the right. The name is going to match the deployment name. So when we did a kubectl get pods, or excuse me, the pod name, it's going to match the pod name. We saw that it's this long thing where it's MSSQL deployment, and then in 5T, that we can see that's the same there. Let's go ahead and create a database, and I'll use SQL CMD to do that again. And inside the quotes there, you can see create database test DB1. And so now I want to bring together where this data actually lives, right? It doesn't live on the node where the pod's running. It lives external to the cluster on an NFS server. And if you were doing this in Azure, it'd be on an Azure disk or some other storage subsystem that you're using. So if I ask SQL Server, give me the physical name of all the databases from sys.master files, run that code. And there we can see on the bottom left here where all of the databases, where SQL Server thinks all of these databases are. So there we see all the system databases in varopt MSSQL. And here we see that when I did a create database statement, leveraging that default database and default log configuration that we asserted in those environment variables, I didn't specify the file locations, but since I specified the default configs, they landed in the right place, /data and /log. If I go onto my NFS server and I get a directory listing from the NFS server itself, and that's what I'm doing here with this command. I'm just saying, you know what, give me a directory listing from this physical location on my NFS server. There we see data log and secrets and .system. If I go inside /data, we'll see all of the system databases. If I go inside of this directory here, /SQL/data, there we'll see our user database, and there we'll see our log database. Now, these all share one storage subsystem for demonstration purposes. Obviously, if we were doing a more advanced disk topology, these would be back-ended by potentially different servers or different disk subsystems and things like that, so that can reap the benefits of having those separate disk infrastructures. But the key concept here is SQL Server thinks its files are at these locations, all right? But it's the responsibility of Kubernetes to mount this NFS share and map that into the pod at that particular file system location. So SQL Server thinks that the data is at varopt MSSQL on that local node, but it's not. It's the responsibility of Kubernetes to go mount that NFS share and attach that to the node and get that into our pod so that we can access that cluster. If there's a failure, that node dies, our workload moves to another node. That NFS mount will just get mounted on that other node when that pod gets scheduled onto the other node in the cluster. So that's how we're able to get that failover cluster-like functionality inside of Kubernetes. And again, going through storage subsystems and things like that, we'll have to get into the details of your particular infrastructure, but just to drill home the concept that we're using shared storage there. So let's do something a little bit different now. Let's look at resource limits. And I want to grab this YAML file now. So this YAML file, very similar to the one that we just rolled out. The difference in this one is I'm defining some requests. So guarantees. I'm telling Kubernetes I want exactly 1 CPU and exactly 4 gigs of RAM for this pod to start up. That's a guarantee. I need that for this workload to run, right? That's what a request provides. Let's go ahead and push that out. When I make that change, right, that's going to stop the pod and start it again. So know that this is not like a zero downtime thing, but we're changing the actual configuration of the pod itself. So if you think about like in a virtual machine, you kind of have to do the same thing, right? To shut it down, adjust its resources, and turn it back on. Now, let's go ahead and check the status of that pod, see if it's back. Oh no, it's pending. Why is it pending? All right, well, let's look a little more closely. What pending means is we're trying to start this pod back up, and for some reason, something's blocking that pod from starting. And we need to be able to figure out, well, why? Like, why is this pod no longer starting? Well, we made a change about resources, so that should be your hint there. There's something wrong with the allocation or the access to those resources. And when something goes wrong inside of Kubernetes, my favorite command to use is describe. So I'm going to use that kubectl describe command against the pod resource. And we'll see at the bottom there in the events associated with our SQL Server pod that we had insufficient memory across all the nodes in our cluster. So 0 of 4 nodes had exactly 4 gigs of RAM to guarantee or to give me to run my pod. So that's the reason why we said, hey, Kubernetes, I need this thing to run on exactly 4 gigs of RAM. Well, nobody in our cluster had 4 gigs of RAM to give. Our nodes, specifically in my demonstration cluster here, have only 2 gigs. And so that's why we were short. So let's go ahead and correct that and push out a corrected version. Inside that corrected version, we'll see I have, let's see, correct. That's this one. Yeah, this one. Yeah, I've reduced it to 1 gig of RAM. Now, if I go and check my pods again, so kubectl get pods up and running, and we're able to affect that change. Let's make sure that SQL Server is up and started by asking for its name. Sometimes this can take a second, depending. Oh, there we go. Good. So there we see 2019 CU5 is back up and running. All right, moving on to the next demo, let's kind of look at HA scenarios. Right, we just looked at resources and limits, resources and limits. Now let's look at high availability scenarios inside of Kubernetes. So shutdown with no wait is a command that effectively tells SQL Server to crash, like ungracefully just shut down right now. And if I do that, and I'm going to basically say, you know what, it's kind of like literally killing the process inside of SQL Server. But what's going to happen? Like, so I told our deployment to make sure that you always keep one SQL Server up and running at all times. And it's going to do that. If I do a kubectl describe get pods, that we'll see about 13 seconds ago, it went ahead and checked to make sure the container image was there. It created the new container and started it back up. So I killed SQL Server, and within a matter of seconds, Kubernetes, more specifically in this scenario, the kubelet was like, you know what? That application just crashed. Let's just go ahead and restart it. And that's from a facility called the container restart policy, which is part of the default pod configuration inside of deployment. That's what restarts that container there. But I also said that Kubernetes, you know what? I need you to keep one pod up and running at all times. So what if I grab my pod name and store that in an environment variable? So that's our pod name ending in mpnlw. If I delete that pod, what's going to happen? So basically a second ago, I crashed the process, and the process is restarts inside the container. In this scenario, I'm deleting the actual API object that is the pod. And I've just destroyed the whole life cycle, right? Remember that concept of going back to that default container. So what's going to happen here? What's going to happen if I delete the pod? Well, the deployment object where we define replicas 1, we said, hey, I need you to put exactly one pod back or running exactly one pod all the time. And what Kubernetes is going to do is it's going to put a pod back for me. So if I do a kubectl get pods here at the bottom, we can see that I have a new pod up and running ending in 2JVW4. It's got a unique pod name when it gets recreated, or when it gets created again as of 36 seconds ago. If I look at sys.master files again and say, hey, what's your configuration? Well, there you go. We can see that I have all of the data that I had a second ago. And so that's kind of drilling home that concept of decoupling pod configuration and pod state from the life cycle of the pod itself. I destroyed that entire pod and deleted it. The pod started back up. It saw that it had disks that it needed to attach. It attaches those disks. The process starts. The process sees it's got a master database, or SQL Server sees that it's got a master database. That master database comes online. There's our configuration. It's like, you know what? I got user databases at /data. Let's go ahead and online those databases and bringing all that back together. Now, from a backup standpoint, let's dig into that demo real quick. I'm going to roll out another configuration where all I'm doing here is creating some additional disks to attach into our pod. It's at /backup. And so let's take a peek at that code. Inside of that code, if you go look in here, all we're doing is attaching another persistent volume at this physical location. And I'm going to scroll down real quick. You can see I added another volume mount for /backup. So all we're doing is attaching another volume at that file system location. And so we can run standard backups to that particular file system location, because now at /backup, it's back-ended by, in this case, my NFS server, but ideally this would be a separate storage subsystem from the primary workload. And if I look at that NFS server, if I do a ls on /backup, there you can see my test db1 backup is now available. But what if I wanted to get a little more advanced? What if I wanted to use some tooling for this? Well, let's use DBA tools to help us with that. Now, we're going to go ahead, and since we switched over to PowerShell, I need to create a credential. And what we want to do here is build the objects that we'll need to authenticate to our cluster. I also need to grab the service IP again, and also the port, because we're switched from Bash over into our PowerShell. We're going to test the connectivity into our instance. So connect DBA instance. And in a second, we'll see that we are able to connect to our SQL Server. And then what we're going to do next is one of my favorite DBA tools commandlets, a backup DBA database. We're going to run that code there, specifying the backup path. And simple as that, again, just leveraging standard tools that we're used to using, driving backups to get our backups done for our SQL Server that's deployed inside of Kubernetes. One command gets us backups of all of the databases on our instance. So really cool functionality there. Let's jump back out into Bash. And if I go and I look at that backup directory on my NFS instance, there we can see the stack of backups that we just deployed together. So very powerful features there. So let's jump back into the presentation and wrap things up. So that's kind of really a lot of demos to walk through things like, deploying SQL Server with persistent storage, disk topology configurations, setting resource limits, HA, and also backing up SQL Server. Why? Why are we doing all of this stuff? Well, when I got involved with Kubernetes, I saw this architecture being presented. I'm like, man, that's complicated. What's going on there? But one of the core values behind Kubernetes is being able to write code to build systems. In this case, a pretty complex distributed system called a big data cluster. Now, I don't want to really focus on what a big data cluster is, other than that it's a collection of SQL servers and other tools that provide this ability to be able to process big data scenarios. But when I got involved in Kubernetes, I saw this big complex picture and I was like, man, how are they going to do that? And I learned a little bit more about Kubernetes, and being able to write code to build systems is how you're able to achieve this type of system. At the bottom of this picture, that's what you see, right? You see Kubernetes. There we see things that we talked about today. We see nodes, we see persistent storage, we see pods and things like that. And so Microsoft is able to build their next generation data platform systems on top of this underlying infrastructure that is Kubernetes. So in addition to big data clusters, we also see this on the Azure Arc data services side of the house. So if you look at that list there on the left, step one to having Azure data services in your environment is to have Kubernetes in your infrastructure. And so if we look at that graphic on the right here, we see, again, at the bottom, we see Kubernetes, we see things like nodes and persistent storage, all those key concepts that we kind of drove home today. And that, for me, is when I figured out that's when I wanted to really invest in learning and becoming an expert at Kubernetes, is when I started seeing these more complex systems coming out from the SQL Server product team, like big data clusters and Azure Arc data services, and how they're building on top of that infrastructure to provide these services to us as consumers of SQL Server. All right, well, that's a wrap for this. We covered a whole big bunch of stuff. We talked about deploying SQL Server in Kubernetes and the key elements that we really want to focus on. So data persistency and storage inside of our cluster. We looked at how to configure pods, right? And running and what it really looks like when you're running SQL Server inside of a pod. We dove into disk configurations and resource configs, backups, of course, and also, like I said, the present of SQL Server and Kubernetes, things like big data clusters and Azure Arc, and how those are built on top of Kubernetes by defining those systems in code. I want to thank you for watching. If you want to dive into more detail about Kubernetes and Linux and SQL Server on Linux, head over to pluralsight.com. If you want access to that content for free, send me an email and I'll give you a 30-day free trial access code and no questions asked. And if you're not already, please go ahead and follow me on Twitter. I appreciate you watching and learning with me. So have a nice day.